Energy, it's the pulse of life. It's what makes the world go round and round. Energy, it's the pulse of life. It's what makes the world go round and round. Round and round. Round and round. Round and round. Energy.
You can have your cake and you can eat it. Make life sweet, it's hard to beat it. What a thrill to be so free when you live better electrically.
Progress used to mean promoting more energy use, but the effect of energy on the environment has brought about a new definition of progress. It focuses on the services that we use energy for, and it measures success by how little energy we can use to provide these services.
5041 protection changed for no reactor operation, eh?
This end-use approach, as it is called, harkens back to Thomas Edison, whose real interest was in providing a better form of lighting, and for whom supplying power was only a means to that end. The best way to lick the energy blues and still maintain a high standard of living is to be more efficient in our use of energy. About a third of all our energy is consumed in buildings for heating, air conditioning, lighting, and appliances. This is the area where energy efficiency could provide the biggest payoff. For instance, in colder climates, about a quarter of all heat is lost through older windows like these, with little insulation value.
Newer windows have technologies like these with special extra layers, with special coatings on the windows, and with gases in the windows as well. And some of these windows are now 4 times as efficient as the windows that you would have purchased just 10 or 15 years ago.
These energy-efficient windows are called low-emission or low-E because the heat heading out the window is reflected back into the room. At the Pacific Energy Center in San Francisco, an infrared camera and TV monitor show how they work. The camera is aimed at a low-E and a regular window side by side, with the low-E window on the left. When someone stands in front of the regular window, his image is barely seen on the monitor. However, in front of the low-E window, his body heat is reflected back to the infrared camera. Energy can also be saved by designing buildings which allow in sunlight during the winter and screen it out during the summer. By reproducing the angle of the sun as it changes from season to season, this swiveling table with its miniature cameras allow architects to test their buildings and actually see how much light will get in as the seasons change. In the summer, with the sun high overhead, the windows are shaded from direct sunlight. But during the winter, when the angle of the sun is much lower, sunlight comes pouring in. This new house in Chilliwack, BC is being built at the cost of an average house its size. Yet it will use only 1/3 as much energy. To begin with, it was oriented for maximum solar benefit. Its rear wall faces north and is shielded by trees and earth from the cold winter winds, while its front wall faces south and is exposed to the sun.
We've got a big expanse of tempered glass here on the ceiling to let the sun shine in. In addition to that, we've got almost complete glass on the south side. And this is high-tech glass. We've got 4 big windows up in the second story. We've sloped the ceiling and we've made it a nice reflective white color. And during the day, it brings in all of that light and lights up this whole central area without any lights actually being on. So we're using daylighting to its maximum.
In addition to being very well insulated, the house uses thermal mass to store the heat it gains from the sun. Thick concrete floors and a central fireplace soak up excess heat during the day and then release it at night. The small amount of heat that the house still requires in winter comes from this pond through a device called a heat pump. It employs the same principle as a refrigerator. Electrical energy powers a compressor, which extracts heat from a source that is cold and then releases it into the house. In this case, the heat pump extracts its heat from antifreeze that circulates between the pump and the pond.
There's a couple of lines come down from the house underground to here. They come down into the pond, and the fluid that's coming down is much colder than the water, so it'll absorb heat from the pond. And even in the middle of winter, when the pond is at like 32 or 33 degrees, the antifreeze can come down here and pick up the heat.
Heat pumps are highly efficient. They only use about a third of the electricity of an equivalent resistance heater, and in the summer they can act as air conditioners by pumping heat in the other direction. Lighting eats up about 1/4 of all the electricity we generate. Another way to think of it is that 1 out of 4 power plants exist for lighting alone. At least half of those plants could be closed, leaving our cities just as brightly lit, simply by switching to more efficient lighting technology.
This is an integrating sphere. It's used for measuring the total amount of light coming out of a light bulb. In order to use it, we put the light bulb in this socket here, and I measure the light coming out in the detector that's located there.
What's being tested in the sphere is an ordinary incandescent light bulb. This bulb is putting out less than 1 unit of light while using up 73 watts of electricity. An incandescent bulb converts 95% of its energy into heat and burns out after about 750 hours. This is a compact fluorescent light bulb, which is 4 times as efficient and will last 10 to 15 times longer. As this test shows, the compact fluorescent produces more light than the incandescent while using less than 21 watts. This is the San Francisco Bay Bridge. It is now lit by 2,000 compact fluorescent bulbs. Over its lifetime, each bulb will save the energy equivalent of 180 kilograms of coal and the emission of a ton of CO2. The local taxpayers will also be saving a ton of money. Bicycling is by far the most efficient way to get around and is totally pollution-free. Driving, on the other hand, consumes about 1/4 of all energy and produces about half of all air pollution. This is Davis, California, where bicycles sometimes outnumber cars. Why are scenes like this so much less common than scenes like this? One of the most profound effects of the automobile has been to reshape our communities, from compact cities where everything is within easy reach, into low-density, sprawling suburbs where great distances separate where we live from where we work, play, or even shop.
It's difficult for people in this community to try to walk to a store, to walk to their schools. It's very low density, and it's very difficult to have a transit facility to service this community because you've got very few people living per hectare. The costs of transit service are high, and there's no incentive for people to walk or cycle anywhere.
How we design and build our communities greatly affects how much energy we consume, particularly for transportation. The automobile has helped create communities that encourage more driving and more energy use. To break this pattern, we will have to rethink how we plan our communities.
We need to look at more efficient land use patterns. We need to look at the way that we try to move people around in a community. We need to look at the way that we site our homes and our neighborhoods to make use of passive solar resources. And I think that adds a whole new dimension to the concept of energy efficiency.
There are potential savings not only in the way we consume energy, but also in the way we generate it. Normally, when a fossil fuel is burned to power a turbine like this, only 1/3 of the fuel is actually converted into electricity. The rest is wasted as heat. This natural gas-powered generating station in Toronto manages to squeeze over twice as much useful energy out of its fuel. It does it in two different ways. First, natural gas is burned in this turbine to produce electricity. Then the exhaust gases, still containing 2/3 of the original energy, are used to boil water into steam to drive a separate turbine. The steam which comes out of the steam turbine, again containing 2/3 of the energy that went into it, is then passed through this pipe under this stretch of ground and into the building next door, which is an airplane factory. Here, the waste steam is used for heating and to help dry the paint on these jumbo jet wings. This process of burning fuel for both electricity and heat is called cogeneration.
A look at history reveals, slowly turning wheels, till we put some steam into our energy. Thomas Edison then said hallelujah, amen, and wired us all for electricity. Along came a moving machine that fed on gasoline, and our travel plans all turned to fancy free. Our cities blazed with light, it was our new birthright to have more energy-consuming gadgetry. But soon those carefree days took on a troubling haze, 'cause of the energy-spending habits we embraced. Our houses leak their heat, our light bulbs really eat that electricity that we so often waste. The way we mobilize is really quite unwise, it's a costly way to get from A to B. When we're behind the wheel in our own automobile, we're on an energy spending spree. Time to change, time to lower our demand before those greenhouse gases get out of hand. Efficiency is common in style. Switching off will save you a pile. Choosing the light with a small appetite to be energy hip, you gotta weather strip. Efficiency is doing it smart. Double the use when you make that juice. Talking about cogeneration. You're talking about cogeneration. Your savings will jump when you use a heat pump. The energy key is efficiency.
The energy we can save through greater efficiency is perhaps enough to buy us several decades of equilibrium with the environment. But eventually, because of growth, particularly in the Third World, we will need more energy. At the same time, our supply of oil and natural gas will be winding down. The long-term solution has to include new sources of clean, renewable energy. Where will we find these new sources? One source is not so new. Wind power has now become a cost-effective source of electricity, but only where there is a sufficiently strong and steady wind. Currently, the world's wind-generated power is concentrated in several valleys in California. The best winds, however, are in the middle of the continent and represent a huge untapped resource. Wind is also plentiful in the far north, where electricity must be generated locally using diesel fuel flown in at great expense. Here in Fort Severn, this windmill helps power the northernmost outpost in Ontario. The rise and fall of the ocean tides is another potential source of energy. This small power plant in Nova Scotia converts the twice-daily tides of the Bay of Fundy, which are the world's highest, into electricity. Fully developed, the tidal energy of the bay could supply 3 times the entire province's needs, but only during the 12 hours a day that the tide is running, and at what is still an uneconomic cost. The enormous amount of heat in the Earth's core sometimes erupts as a volcano and sometimes percolates up as superheated water. This geothermal energy can be brought to the surface where it can drive an electrical generator. In those scattered locations where the geology is right, geothermal is a clean and economical source of power. This geothermal plant in the Mojave Desert is part of a complex that can supply cheap electricity to a city of 1 million people. A source of renewable energy found almost everywhere is garbage. Much of it is derived from the fibers of living matter, which makes it an example of a type of renewable energy called biomass. At this landfill in Pickering, Ontario, the methane that results from the decomposition of the buried garbage is sucked out of the ground and piped to this nearby power plant, where it is burned and converted into electricity. Perhaps the most promising renewable of all is photovoltaics, the conversion of sunlight into electricity within wafers of treated silicon. This is the world's largest photovoltaic installation in Sacramento, California. It sits in the shadow of a problem-plagued nuclear plant, which once supplied half the city's electricity and which was shut down by the local voters. To help make up the resulting shortage, the local utility, called SMUD for short, turned to renewables, particularly photovoltaics.
Photovoltaics has a range of advantages that make this a very useful power source for a utility. First off, it's modular, which means we can put it in small blocks at a time as we need the additional power in very short time spans. We don't have to plan 10, 15 years ahead and guess what our power needs will be.
Although they currently meet only a very small fraction of our needs, it is not hard to see how renewables might one day supply much of our electricity. But what about that 1/4 of all energy that's used in transportation? How do you power a vehicle with wind or solar energy? One possible link between renewables and transportation is the rechargeable battery. This is a photovoltaic panel in Sacramento used to recharge electric vehicles. SMUD is now heavily promoting electric cars and even thinking of manufacturing them.
Sacramentans are very excited about the possibility of electric vehicles in our future. You know, 70% of the air pollution in Sacramento comes from gasoline-powered automobiles. So people here are looking for a real alternative, and they'd like to make a personal contribution. We think cars like this one are a way that everybody in Sacramento could help clean up the air.
But the electric car is far from a new idea. In fact, the first cars were battery-powered, and they once dominated the market.
Well, actually, it was the electric starter that was the demise of the electric car. As soon as they were easy to start, gasoline engines became a little more popular, and they could be refueled in a few minutes and driven for greater distances.
In spite of much research, the best rechargeable battery still can't match the convenience and economy of the gasoline-powered engine. There is another, more promising way to power a car from renewable sources. It uses an energy-rich, non-polluting fuel, which also happens to be the simplest, most prevalent element in the universe: hydrogen. The use of hydrogen for transportation started off with a bang. In 1937, the airship Hindenburg, inflated with hydrogen, crashed in flames. But when the space era began, it was hydrogen in liquid form that powered the rockets into orbit. Hydrogen packs more energy per gram than any other fuel.
basically the staple fuel of the space program has been hydrogen. Now, to draw a parallel, to go one other thing, if you look at when gasoline really began, we think of it in cars, but it was really airplanes. You couldn't fly an airplane using coal. Do you see what I mean? You had to have gasoline. So you developed those fuels for airplane, which in those days was the toughest thing to do with transportation. And then people got saying, hey, that's a pretty good fuel. Let's make sure we use it in automobiles. And then later, trains switched from coal to diesel, which is kind of like the gasolines. My view is exactly the same thing will happen with hydrogen. It was the only way we could fly to the moon. It's going to be a very good way to fly airplanes. Sooner or later, it'll be on the street.
This bus, built in Vancouver, runs on hydrogen. But instead of burning it, it combines hydrogen with oxygen in something called a fuel cell. A fuel cell is twice as efficient as an internal combustion engine running on hydrogen. Like a battery, a fuel cell produces electricity, but there are some important differences.
A fuel cell is like a battery in that it has a positive and a negative electrode. But whereas in a battery, the electrodes are actually consumed in making electricity, in a fuel cell, the electrodes are unchanged. What's consumed is the fuel and oxygen from the air. So long as I continue to supply the fuel cell with fuel and air, it makes electricity. In order for the electrodes to work, there has to be an electrolyte between them. That's completely analogous to the acid in the battery in your car. But in our fuel cell, we replace that acid with a piece of plastic. We take carbon paper, apply a platinum catalyst to it, and then sandwich that electrode on either side of the electrolyte to produce this unit, which is in fact the fuel cell. If I supply hydrogen to one side, air to the other, we'll make electricity and water.
The fuel cell was invented in 1839, but it was ignored until the U.S. space program adopted it as a portable source of electricity and drinking water for its astronauts in space. Hydrogen is clearly a very efficient and clean transportation fuel, but how does it link transportation to renewables? On a rooftop in Toronto, the hydrogen filling this balloon is being produced by the energy of the sun. What happens is that when sunlight hits a photovoltaic panel, the resulting current is fed into water through two electrodes. This electrical energy begins to split the water, producing hydrogen bubbles at one electrode and oxygen bubbles at the other. This simple process, called electrolysis, can produce hydrogen using any form of renewable energy.
The key issue is that hydrogen will allow you to use whatever energy source you think is the most suitable and most environmentally benign. And then once you've got the hydrogen, you can fly airplanes, you can drive cars, you can run buses, and all those sorts of things. So you see, it really is the solution. And the curious thing is, I've thought about this for roughly 15 years, and I keep asking people, can you conceive of another way to do this? There isn't any other way to do this. Sooner or later, the world will have to go to hydrogen for driving its transportation systems, and that hydrogen will then open up all these opportunities to harvest whatever source you like.
We can no longer take nature's liberating gift of energy for granted. We must begin making wiser choices, both in how we use our energy and where we take it from.
There are new and old sources we can use to get powered. They'll generate clean energy and not be devoured. From capturing the wind to a hydrogen cell, to harnessing the sun and all the places we dwell. We must learn how to live with more alternatives. Energy, it's the pulse of life. It's what makes the world go round and round. Energy, the single theme of life that weaves everything into common ground. Energy, it's the pulse of life. It's what makes the world go round.